Hi, welcome to Izzy in Space. I'm Izzy, and I'm a theoretical physicist who studies gamma ray bursts, the brightest events in the entire universe. If you've been watching the news, or maybe you've seen my previous video, then maybe you've heard of NASA's Neil Gehrels Swift satellite. If not, there's currently a really exciting effort being made to try and rescue this satellite by boosting its orbit to prevent it falling back to Earth and being lost later this year. And if you want to learn more about this rescue, then go and watch my video, NASA's Swift Rescue Mission, all about it. Today, though, I want to talk about why Swift is so special and why we're so determined to try and rescue it. So Swift is designed to find gamma ray bursts, or GRBs, which are the very events I research. So maybe I'm a little biased, but I think it's definitely worth all the effort to try and save it. And hopefully, in the next 5 minutes, I can convince you that it is too. GRBs are so bright, they outshine whole galaxies. They have a power equivalent to that emitted by the Sun across its whole lifetime, but released all in a matter of mere seconds. They can help us learn what happens in the deaths of giant stars and when neutron stars collide, where elements essential for life are created. If you want to learn more about them, then follow this channel, because I'll be uploading a video all about them soon. Swift has been instrumental in finding GRBs all the way back to 550 million years after the Big Bang. That's more than 13 billion years ago. And over its current 22-year lifespan, Swift has discovered 1,760 GRBs. It finds these GRBs using 3 different telescopes it has on board. The Burst Alert Telescope, or BAT, continuously scans the entire sky, and as soon as it sees the signal of a GRB, it sends an alert to our computers. And once BAT finds our signal, Swift automatically slews, or turns in space, to point its X-ray telescope, XRT, to the source. Now, Swift is particularly remarkable because of how fast it can perform this slew. Once a signal has been detected, the satellite turns within 20 to 90 seconds. That's less than the time it takes to brush your teeth for its longest turn. No other telescope has ever been able to even match this timescale. The initial signal of a GRB lasts only seconds, so this fast slewing time is a very important feature and part of what makes Swift so special. Capturing this initial signal allows us to better understand the origin of these insanely bright events and follow the GRB for the next few weeks as it continues to emit lower energy light. My work in particular focuses on this early time initial signal of the GRB, and hence this fast reaction time is absolutely essential. Otherwise we can miss this crucial part of the signal and then, well, I can't do my research. Swift's final telescope is the Ultraviolet and Optical Telescope, UVOT. UVOT's particular skill is its ability to pinpoint the location of the GRB on the sky. UVOT achieves sub-arc second localizations. Now you might ask, what does that mean? GRBs are so far away from us, far outside our own galaxy, that they appear as a single dot in the sky. But determining their exact position is very, very hard. Swift, however, gets very close. Our telescopes can tell us that a GRB occurred within a certain area on the sky, which we measure from Earth as an angle. To get the best accuracy on the position of the GRB, we want this angle to be as small as possible. And Swift is able to narrow down the GRB location to within an angle of less than 1 arc second. This is an astrophysical unit, and it corresponds to 0.00028 of a degree. That's up to 100 times more precise than NASA's other GRB satellite, Fermi. Hence, Swift is very special, and we do not want to lose it in its unique capabilities. These space-based satellites send alerts direct to our telescopes on the Earth, so they can scan the sky to try and find the GRB from Earth as well. So Swift's ability to narrow down the size of the area we have to search makes this process much easier, increasing our chance of seeing the GRB from Earth's surface. A particular telescope I work with is called GO2, and this automatically ingests the alerts from Swift and Fermi and turns to the location in the sky without needing a human to trigger it. This allows us to catch the GRBs as quickly as possible after the alerts are sent. Now, earlier this year, Swift turned off its telescopes to save power and improve its chances of survival until the rescue arrives. However, Since then, it's become much harder to follow GRBs from the ground because we have to search a much larger chunk of the sky. So we are very keen to save Swift and stop having to search half the sky for each GRB. So, hopefully, I've managed to convince you that with its unparalleled fast slewing time and precise location pinning, Swift is indeed a very special satellite and well worth a revolutionary rescue mission to save it.